recording this session, and we're going to go into the new material. And before we go into my PowerPoint, where's the chat? Okay, I'm going to take attendance a little bit differently this time. So I will please ask you to all write present on the chat after I just wrote attendance, and I'll just use the transcript of this session to take attendance. Okay, so go on and write it. And now I want to ask your experience with the pre-test. Was it difficult? Was it stuff that you already knew? Any opinions on the pre-test? Oh, by the way, I already also released the scores, because I think after your attempt, you cannot immediately see your scores, 100 or whatever. But now I think I've already released them, so you can go check and see maybe which you got wrong, and we can go through them if I can figure out how I can display this quiz on my screen. Can I attempt it? I cannot attempt it. Wait a minute. Okay. I can show you the review of my attempt, which is, show you that. Okay. I know we haven't gotten into the material, but I do believe some of these things are already known to you. So for example, number 1, if the probability that it will rain today is 0.8, how large is the probability that it will not rain? So most of you got this right, I believe, 0.2. Would anyone care to help me out and add on to how I could get the 0.2 here?
1 minus 0.8.
1 minus 0.8. Very simple, right? Because I'm talking about a certain event that it will rain and the event where it does not rain. So it's complement or its opposite. You can remember perhaps your discrete mathematics knowledge here. And the next one is if the intersection of event A and event B is an empty set, that means that nothing that happens in event A and nothing that happens in event B are the same. They both can be described as mutually exclusive. Yes, the correct term is mutual exclusivity, and we're going to look into that with more detail later on today. The next question. If the probability of E, a certain event E, is 0.5 and the probability of F, another event, is 0.5, then the probability of E or F, either one happening, must be 1. The key here is the word must. So if I have one event, 0.5, another event, 0.5, when I say the probability of E or F, 1 makes sense in a way because I can just add them up, right? E is 0.5, F is 0.5. So either one would be 1, right? But there is a certain case in which it is not equal to 1. We're going to look back into that. We're going to look more into that as well later on today. I do believe there is one person that got question 3 right. I'm not going to show it to the class, don't worry. You can't see my screen that has all the results, right? Or can you? Am I just, can you see?
No, we can.
Okay, great. Don't want to expose any of you. Okay, let me check. I think I do remember someone getting this answer correct, and I'm gonna call you out. Quiz 3. Quiz 3 attempts. Um, Avatar. Yes,
Yes.
Avatar. Avatar got that one correct. Can you explain to me why you said that it might not be one?
Because there's a possibility that E and F are not mutually exclusive. They could occur
Exactly.
at the same time.
Correct. It has something to do with the question before. It's because like if they are mutually exclusive, then yes, because they don't have anything to do with each other. But what if they have something in common? Like maybe an outcome is they share an outcome. Thank you very much. Next, question 4. Which one is not correct about the sample space? We're going to go into more detail here, but the correct answer is the sample space is a subset of the outcome of an experiment, which is false because the opposite is correct. The sample space is the outcome of an experiment is a subset of the sample space. Next, this statement is true. The probability of PE equals 2. This is a false statement. Would anyone like to give me an input why this is incorrect? Who got this right? Let's see. Aha. I have a correct answer. The first person that's coming up here. Dito, Fauzan Hanan Dito. Why is this incorrect?
So the probability range is between 0 and 1.
Yes, exactly.
Okay, that's
okay. Exactly. So the probability is measured in 0 till 1. Sometimes you can also use percentages. You can also use fractions. It doesn't really matter, but the value is between 0 and 1. Great. So actually, you guys already know a lot about this. The average score is quite great. It's quite good. So I'm not that scared to go into the material this week. Okay. So this week we are going to talk about elements of probability or basics of probability. And we're going to discuss the different types of probability you know, how to compute them, and how we can describe them mathematically. I do bet that you guys already know what I'm talking about, but we're going to try to define it in a constant and correct way. So since I'm going to go into the materials, feel free to turn off your camera now if you're not comfortable leaving it on. But if you want to keep me company, by all means, thanks, you can leave it on as well. Okay, so we already talked about descriptive statistics. Last week, we finished that chapter when we were talking about how we can describe our data, how we can present our data. So the first step that we needed to do is sampling, because I cannot obviously study the entire population. It's physically impossible for me to do. After obtaining the sample, I can then describe my sample using descriptive statistics. But as we know, the data itself is not much of a use to me because I need to get information from it. I need to translate this data into something that can be useful for whatever task or whatever intentions I would have. So that's the next step. In the next step, we would like to infer something. We need to make a decision. We would like to take an informed decision about this particular task that we have in our consideration. So in order to do that, we need to know some basics of probability that will describe the underlying distribution of our population. So this is the outline of this chapter. I've tried to divide it into 6 different sub-chapters that you can see here. If you already did the pretest, you probably have already seen these slides as well. I'm going to try to go through at least up until the Bayesian rule, because it's important, I believe, and you can read on your own the remaining subchapter of independent events. So we'll see how fast we can get, but I'm going to try to finish up to the Bayesian rule today. Okay, so this has something to do with what we talked about in the quiz about the sample space and event. I also already gave you a hint. I mentioned that we need to remember your discrete mathematics knowledge. So we're going to talk about subsets and sets and the universe and so forth. We're going to bring out our Venn diagrams once again and understand the relationship between the different sets, or in our case, the different event spaces. Okay, let's start with the definition. So the sample space S is a set of all possible outcomes of an experiment. So what does an experiment mean? An experiment is any process or procedure for which one outcome is possible. So when we're talking about probability, two words come to my mind. First of all is uncertainty. Oh, sorry. First of all, it's uncertainty. Let me change the color. Ink color blue. And pen. The first word that comes to my mind is uncertainty. Because I don't really know what's going to happen when I do something, when I have an event. In this case, it's my experiment. We don't always know, we don't know for certain what is going to happen when I do my experiment. Second of all, another thing that comes to my mind when I'm talking about probability is chance. So since I don't know what might happen, I want to know the probability or the chance that something would happen. Like if I know that there are two possible outcomes, what is the probability that this one happens? What is the probability that this one happens, and so forth? So this uncertainty allows us to model our problem so that we can measure we can measure and we can consider the possible results of whatever I am attempting. You've heard of this before. So like if I were to attempt to toss a coin, heads or tails, actually, an Indonesian coin doesn't really have heads or tails, right? It's not a head usually, but you get my gist. On normal coins, most coins, we have either heads or tails, the numbers or the face or the drawing or whatever. In that case, there's only two things that could happen if I throw my coin. I can define my sample space or my universe as a set of heads and tails. Nothing else would happen. So in that particular universe, my sample space is heads and tails. There's no other thing that could happen. Next, if I'm talking about the race of these 6 horses, then and I want to know the order, then my sample space is all the orderings of 1, 2, 3, 4, 5, and 6. And last example, if the experiment consists of determining the amount of dosage, then I can have 1, 2, 3, 4, and so forth until infinity. So you can notice here that up until now, I've been using the set notation to describe my sample space. Because indeed, my sample space can be notated as a certain set, which is my universe. So if I were to say, where's my pen? So if I were to say that my sample space like this, if you remember the Venn diagram, this is my sample space here. You can use the letter S here. This box contains all of the possible outcomes to my experiment. And then the event is what actually happens. And this obviously is a subset of my sample space S. If the outcome of my experiment is contained in E, then I can say that E has occurred. In the case of heads and tails, then my S only contains 2 data points, tails and heads. So in this particular case, the way I drew this is that apparently when I threw my coin, heads came up. So if I were to write these events, the event that an even score came up, then the event is as follows. The event that I got heads is as follows. And the event that number 3 horse wins the race, all outcomes or all orderings that start with 3. Once again, please keep in mind that we use the correct set notation. So I use my curly braces and not any other type of braces to denote the set of events as well as the set of my sample space. Do we have any questions up until here? I'm gonna take a pause to take a drink. Anyone? Nope, still simple? Okay, good. So now, since we've already used set so many times, set notation, set theory, let's remember all of these particular terms in set theory. Remember your discrete mathematics. Okay, here, what do we have? Have some particular terms here. I have union, complement, union, and then I have intersection and subsets. I hope you all remember what I'm talking about. First of all, say we have sample space as such, and I have a certain event, E, like that. So if I have E here, how can I define E complement? Anyone? This is E. I want to know E complement. Anyone? Which one is E complement on my Venn diagram?
Basically outside E.
Anything outside E, right?
And inside S.
And inside X. Good idea. If not, I'll just write all over the whole slide, right? So anything outside E, but inside S. Yep, that's right. Next, union. Union. So now we're starting to talk about 2 different events. So when I'm talking about 2 different events, this is my sample space. This is event E, and this is event F, E and F. Say it's like that. The union of E and F, E and F, don't forget, the notation is like that, is obviously both of them together. So in my question, when I asked you if E is 0.5, probability, and F's probability is 0.5, is the sum of both always 1? In this case that I'm showing you on the screen right now, yes, it would have been 1. But what happens when my E and F are something like this? Aha. I know now that E was 0.5, F is 0.5, but something is in common here. So if I were to add them up, E plus F, I cannot just simply add them up because I need to minus something here. What do I need to subtract here? This area is common, right?
Intersection of E and F.
Exactly. So I need to then subtract the intersection of both in order for me to obtain the probability of the union. Since you've already touched on, that is actually our next question. Which one is the intersection between both E and F? I'm not going to draw it again, okay? It's just obviously this area here. And if you recall the mutually mutually exclusiveness. Mutual exclusiveness happens, not in this case, but the drawing I showed before, when E and F are completely separate or they are mutually exclusive. What happens to their intersection in that case? If I have,
It would be 0 or no.
it would, yes, so here, like in this case here, when I have, sorry, I shouldn't have drawn it. Can I redo it? No, I cannot. I have to erase. Okay. Here. Pen. Yep. So when I have an S and I have, sorry, I have an, no. When I have an E here and an F here, and I know that they are mutually exclusive, then their intersection is not 0, but an empty set. Don't forget the notation for empty set is you have to cross through your 0. And lastly, about subsets and proper subsets, I want to ask you which of my statements are incorrect. So is this correct? What do you think? Is this correct? AB is a subset of ABC. Is this correct? Anyone? It's correct, right? But what about this? Can I write this too?
Yes.
It's the I can still write it like that. I can actually. But what about this? A, B, C. What about this one? Can I write this?
No.
No.
Can that? It's equal, right? Is this equal to that? It is equal. So actually I can write it like that. But if I were to write it like this, do you think that'd be correct?
No.
No, this is a no. I cannot write it like that. So, sorry, I'm going to show one more thing. Where's my pen? Oh. Why can I not end my slideshow? Oh. So here, these are two different notations. The subset with an equal is a subset. Don't forget that every set is a subset of itself. So if I say like my entire universe is all international student class in my international class students in this Statprob class, sorry, the entire set of you guys are also a subset of my previously defined set. So in this case, we have to differentiate them. And although this is a correct subset, it is not a proper subset. So be careful between these two notations because they don't actually mean the same thing. And once again, if they are subsets of each other, then we can also define them as equal. And lastly, I'm not going to go through these once again because I think you've already met them at least twice in your discrete mathematics class. So we have some different laws that can define the relationship of the algebraic relations between the different sets. Any questions? This means no, I hope. Okay. Because up until now, what I've talked about, I think you've already met or you've already seen at least once before. So I'm going to continue now on the axioms of probability, the definitions, and the rules that come up as a result of the probability principles. So how is it that I can compute, like when I'm talking about the probability of it to rain, I'm looking out my window, that's why I'm looking that way. What is the probability that it will rain today? Well, there are two possible outcomes to this question. It can either rain or not rain, but I want to measure how big is the possibility, how big is the chance that it would actually rain. What would I need to know in order to make an educated guess on that number? Like I could just throw out a number, right? Oh, there's 0.4 probability that it'll rain today. But instead of just throwing out a random number, the concept of probability, I need to know something beforehand. Do you have an idea? Like what do I need to do? Or what information do I need to gather in order to be able to take an educated guess?
See the weather app, I guess.
Okay, I could look at the weather app, but do you know what does the weather app get its prediction from? It tells me, oh, there is a 60% chance for it to rain today. How does the app know?
Previous data.
What data? Good idea. Dito, what data?
Cloud patterns.
Cloud patterns, okay, so they can infer it from other patterns. What else? Like, would it be logical for me to say, oh, I live in Bogor, so it'll probably rain today. How do I know that it would rain because I'm in Bogor? What do you know about
maybe like
Bogor?
geographically, something like that.
That's true. And
Previous data.
sorry, who's just said that? Previous what?
Previous data,
Previous
like
data?
from before, we predict the outcome.
Good. So I'm going to put this together to two main things from your answers. First, you said from other factors or other information, like maybe the cloud patterns, maybe because it's dark out today and so forth. And the other thing is because of past data. You know that Bogor is called Bogor Kota Hujan because from history, it has rained a lot. So the question that I asked in the beginning, I wonder if it's gonna rain today. What's the probability of it to rain today? It has happened for multiple days, over multiple weeks and multiple months and years of people calculating the probability of Bogor having rain today. So when my experiment, in this case, my experiment is it going to rain today? This experiment, if it is constantly repeated under the exact same conditions or roughly the same conditions for any event E, it will converge to a certain constant value with a larger number of repetitions. In my previous example, if we're considering the probability of raining every single day over the past 3 years, 4 years, 5 years, then repeating this experiment every single day, I can predict with a good confidence, with a good educated guess, how big is the probability that it would rain today. So this probability that I'm talking about, the chance or the proportion or the fraction of this happening is called the probability of event E, which we write using the letter P and the normal brackets E inside. How likely will the event E occur? So as a result, all right, that arose from this definition, we have 3 axioms coming out about this probability. We already touched upon this when in our quiz. Dito already told me for axiom 1, the value of probability will be a certain number between 0 and 1. You can also write it as a percentage, you can write it as a fraction, but the value must be between 0 and 1. Next, the next axiom 2 is that the probability of the entire subset equals to 1. That makes sense because in that particular case, we're talking about the probability of everything happening is 1 if you sum it all together. And lastly, for axiom 3, for a sequence of any mutually exclusive events, of a sequence of them, if I were to sum it up, then I can also sum up the probability by just adding them all together. Based on those three things, we now have some propositions. Okay, so now if I have an experiment, I'll put on my pen first. So if I have an experiment, we already decided that the probability of my entire sample space would be 1. Do you remember just now beforehand when we were talking about sample spaces? This is my sample space. This is my event. And everything outside my event was called the complement. Remember this one? Just now we talked about this. So if we all agree that the axiom that we had before says that the probability of the entire sample space equals to 1, then I can also say my probability of E happening plus the probability of E complement happening will also equal to 1. Makes sense, right? Because my entire sample space itself, the entire S here in my Venn diagram, let me change. Ooh. The entire Venn diagram consists of my event E, and everything else is E complement. So now, since I know that, that gives me a conclusion that I am able to compute the probability of E complement given I know the probability of E. What did I do from here to here? Nothing. I just put these around. It's just a mathematical equality. So this has something to do with the question on the quiz that told me if I know that there is a 0.8 probability for it to rain, that means that there is a 0.2 probability that it will not rain, because the event of it raining and the event of are complements. Next, for my proposition 2, since I knew, we already touched upon this just now. Since we knew that the sum of, if I were to compute the probability of E or F, it would be as simple as adding up the probability of PE plus PF. But I think it was Saddam just now before talking to me about, no, we can't, because we have to consider this wedge in the middle here. So in order to compute that, I need to also consider what they have in common or what they have in their intersection. Then I can compute the probability of the union by adding them up minus the probability of their intersection. I believe on the slides, the long slides or the modules, I have all of this there. And there's also one slide that shows the proof of this proposition too. So it is still crucial at this point of statistics and probability for you to remember how to use your set operations that we already talked about previously, the distributive law, the associative law, as well as De Morgan's law. So you might want to brush up on those a little bit, look to your discrete mathematics notes in case these questions come up during Statprob. Okay, so just now, the example I showed you with E and F, I'm only talking about 2 different events, but obviously the outcomes we're not always talking about just 2 different outcomes. We can have multiple outcomes, O1, O2, and so forth. Just that we know that every single outcome must have a probability value between 0 and 1. And if I were to sum all of them up together, then they would equal to 1. Obviously, because if I were to talk about a big subset like this, Don't forget, the probability of my entire sample space equals to 1. So if, for example, this is my O1, this is my O2, this is my O3, O3, this is my O4, and this is my O5, it is quite clear that obviously the probability of all of them equals the probability of my sample space, which is 1. So it's actually very, very, very simple. At the end, what we need to know is that the probability of an empty set equals 0, obviously, because there's nothing in it. The probability of the complement, we also can compute it based on the axioms. The probability of the union, as well as if A is a subset of B, then the probability of A must be less or equal to B. When is it equal? It is equal when A is equal to B. These are the main points. Any questions? Questions? Okay, then I'll ask the questions. First exercise. Before I show you the answer, I'm going to ask you to try it out on your own. I'm going to leave you to it, and I'll get back to you. What time is it right now? 2:17 on my computer. So at 2:20, we'll get back to you with the answers. Okay, it is 2:20 on my computer. So I tried to help you out and translate these two events. Don't forget to write your notations correctly. So there are two ways that you could have notated this. So you could just write P, the student passes math. You could write this, right? But wouldn't that be tiring for you to write this every single time and every single line of your answer? Actually, no, because you're using your computers, right? So you could just copy and paste it. But you know what I mean, my argument. So a lot of the time you can define it as a set. Like in this particular case, we have defined two sets. First of all is the event, the set that shows the outcomes of the event when the student passes math, and B is the event where the student passes biology. I would like to remind you that if you are to use any letter here, you don't have to use M and B. You could use A and B, E and F, but you have to define what you're talking about. So if you were to use A and B, you have to define on the very top what is A and what is B before you do so. So here, obviously, the probability of the student passing math is 2 out of 3. The possibility of him passing biology is 4/9. But let's translate the other sentences. The probability that he passes both courses is 1/4. So what are we talking about here? We're translating this, right? So the probability that he passes both math and biology, so we're talking about math and biology, it is 1/4. And what is the question actually? What are we asked to compute? At least one course. So what are we talking about here when we're talking about at least one course? Anyone?
Union.
Union, because we're talking about either, right? Either passing math or biology. Since we already found from our axioms, anyone? What do I need to do? The probability of math?
PM plus PB minus
the
intersection.
The intersection. Okay, anyone have computed it yet? I don't have my calculator out right
31, oh wait, only the result or
okay, one by one, just to make it clear.
2/3 plus
4/9 minus 1/4 equals?
31/36.
31/36. I do believe I have the answer here. Oh, now it's covered by my annotation. But yes, it is indeed 31/36. Okay, I hope that's clear enough. You can use their axioms, obviously, since we're talking about math here. You have to maybe combine them in some way and turn them around, but you can use those axioms to solve your problems. Okay, now this is just a question. What do you think? What's the probability of a certain dice to show the number 5? What number would you put on that? 0.5?
1/6.
1/6.
1/6. Why do you say that? How big is
Because the total of the CC dice is 6, and then the number 5 is only 1.
Okay, so from your answer, Jerome, we've already defined the sample space, right? You said there are 6 possible sides to the dice. So this is all outcomes. I'm going to introduce some terminology. All outcomes, or this is my size of sample space because I have 6. And this one on top, we sometimes often call this our favorable outcome because it's the one we are currently thinking about. It's the one that we want to happen, the one that we are currently computing. Sometimes we call it the favorable outcome. So you guys said it was 1/6 because logically you have 6 sample spaces and you have 1. But there is a very crucial assumption that you need to have in order for you to be able to take that conclusion. So we have to assume that in our sample space, every single outcome has an equally likely possibility to happen. So like we consider the number 5 to be 1/6, the dice showing number 1, 1/6, and so forth. What if I have a bad die? You know that in gambling, they have something called a weighted die? No, I haven't gambled. I just heard about it. But there is a die that is weighted on a certain side so that a favorable number can come out. So in real life, you cannot always assume that every single side of the die will come out 1 times out of 6. But all of these computations that we are going to consider from here on out, we are going to assume by default that every point in the sample space is equally likely to occur. And thus, in order to compute the probability of an event, I can just compute the number of members in E in the example I just showed you. That means number 5. I know here that, where's my pen? Where's my pen? Hello. I knew that E was the event of showing 5. So I knew something like that, right? And I knew that my sample space was 1, 2, 3, 4, 5, 6. And thus I could compute my PE by computing the number of members in E over the number of members in my sample space. This is an assumption. You have to know that in real life, it's probably not going to, it's not probably, it sometimes does not follow this rule. So as an intuition, if a family has 3 children, find the probability that two of the three are girls. So I first need to consider all of the possible outcomes, right? I need to know what combinations could happen. Boy, 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 girl, and so forth. Among those, I know that there are 8 outcomes, and each of them has a probability of 1/8 because all of them are 8. And in the event that we found that 2 of the 3 are girls, this is my event space, and thus I can compute the probability of events happening as 3/8. Here, I have a crucial assumption, which is right here, that each probability is 1/8. Obviously, in biology, you know that due to genes, that this is not always equal, and due to the X and Y chromosomes, it's more likely for a baby to be a girl. But since we're talking about the mathematical side of it and not the biology, we're just going to assume that the probability is the same for every outcome. Okay, in this particular example, we considered all of these outcomes, right? So I knew that in my sample space, I have boy, 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 girl, boy, girl, 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 girl. What else do I have? Boy, girl, boy, boy. Anyone? Girl, girl, boy, girl, boy, boy, girl, girl, girl. Am I correct here? I know that there are 8, right?
You put girl,
Did I
girl,
put something
girl
twice? Which one?
Girl, girl, girl.
Oh, sorry. Okay, so this should be I'm missing one. Can you imagine if I had not just boy and girl, but I had 6 different colors of balls that I have to combine? Do you actually want to write out every single possibility every single time? Obviously no. Just now I already missed one. Since on my slides I know that there are 8, but if not, I would have mistaken and only written 7, right? So obviously the correct way of computing it would not be for me to write them out one by one. But I'm kind of curious now because I'm missing one. Does anyone realize?
Seto already answered, Miss, in the chat. It's girl,
sorry.
boy, girl.
Girl, boy, girl. I can't see the chat while I'm screen sharing, so you can just unmute it if you want to add on. Thank you, Seto. So it's what? Sorry, girl, boy, girl. No. Yes, girl, boy, girl. So as you can see just now, only 8 outcomes, I've already lost track. But what if I have more? I would even be even more lost. So instead of actually figuring out all of the possible outcomes, it is easier to just use some principle of counting. The first one is called the product rule, as you can see here. In a sequence of R experiments, 1 K possibilities, second K2 and K3. The total number of possible outcomes is just a multiplication of those outcomes. Like for example, how many possible outcomes would come if we toss a coin? How many? Toss a coin? Heads and tails? 2.
Yeah, yeah.
And then subsequently, right after I roll a die, I have 6, right? So I know that my sample space should be the size of 12 in that particular one. What did I do? I had my first event, tossing a coin, 2 possibilities. Second event, rolling a die, 6 possibilities equals 12. As simple as that. But it's not always that simple, right? So we have our friends, permutation and combination. Why are you flinching, Jerome? I just saw your face just now flinching. So we have our permutation and combination. I do think you've seen this before, maybe in discrete mathematics, maybe in calculus. And permutation is a arrangement of objects in a specific number, in a specific order, like, and it's also written as Pn over K. So here I need to take a permutation of K objects from N. So I have a total of N and I need to take K in a specific order. Next, I have combination. So now out of K objects, I need to take a size group, but I don't need to think of the order. Like it doesn't matter if I select Jerome first, then Saddam, or Saddam first and then Jerome, it's the same case. So please remember the permutations and combination rules. We have factorials here, right? This little exclamation point, it shows it is the factorial. What's the factorial? Easy. What does 5 factorial mean? 5 times?
5 times 4, 3, 2, 1.
3, 2, 1, perfect. Okay. A good idea of permutation, of a factorial would be if I were to want to put you guys in a row. Say I have Zahran, Saddam, Seto, and Alifiandra, 4 people here. So in a row of 4, where's mine? In a row of 4 chairs here. Remember the classroom in your international class? Miss it yet? Miss campus yet? So in a row, I believe there's probably 4 to 5 chairs in the new building. So if I were to sit you guys in a row, so if I were to put any one person in the first one, there's 4 possibilities for me to put you there. Next, obviously, there's only 3 left because the first one already is sitting in the first seat. 2 and 1. So this is the easiest illustration of a factorial because I'm trying to combine you in a certain way. Okay, so please recall these permutation and combinations. Ta-da! So for example, a committee of 5 people were to be selected from a group of 6 men and 9 women. The selection is made randomly. So what is the probability that a committee consists of 3 men and 2 women? Recall, my rule is that when I'm talking about the probability of my event, what I need to put as the denominator, am I saying it right? Yes, the one on the bottom is denominator, right? Denominator. Please correct me if I'm wrong. I have not taught calculus in English yet. So the denominator is the total amount of possible outcomes. So when I'm talking about the total amount, what I need to know is I need to take 5 people out of 15 options. So that just means that I need a combination of 5 out of 15 because when I'm selecting, I don't really need to have a certain order, right? It doesn't really matter who I'm choosing first. So I use a combination and not a permutation. And what I want to know is the probability that the committee consists of 3 men and 2 women. So here I'm using the multiplication rule. Yes, the multiplication rule. So the first event that I'm considering is that there were 3 men selected. 3 out of how many? 3 out of 6, right? So here I have combination of 3 out of 6. And I have 2 women out of a possible 9. So using the multiplication rule, event 1 and event 2, I just need to multiply them. So this is my event over here. Combination of 6 and 3 times 9, combination of 9 and 2. Okay, I do not have my calculator here either, but I do think that you can compute your factorials and your combinations automatically these days on a calculator. Does anyone here still use a calculator, or do you just use your laptops or your cell phones? What do kids use these days?
I'm here using phone.
Using your phone. Can you compute scientifically on your phone?
Yes, just
Yes.
download an app. Yeah.
Oh, you have to download an app. Okay, let me look at my phone. Now I'm curious. Does my calculator have a scientific function? It does not. Oh, it does. Okay, I just figured this out. Thank you. So on my calculator, on my phone, also has a factorial function, but it doesn't have the combination as well. So I'm just going to trust myself that this computation is correct, and I have 240 over 1001. Okay, so I'm going to, sorry, no. So I don't want to show you that yet. I hope you haven't seen it. So I want to show you guys this idea here. I want to show you these. Does any one of you know Eddie Wu on YouTube?
I do.
Yeah, I do.
Who's
Discrete
that? Yeah.
math.
I do.
Yes. Have you watched his videos? I'm a fan. So I wanted to present this to you using an example I saw on his YouTube channel. You can look him up if you are interested for more math videos and explanations. He does a much better job than myself in explaining mathematical questions. Go look him up. I wonder how much I'm getting paid for promoting his YouTube channel. I'm not, but I do recommend you to look it up if you're interested to know, especially some concepts about algebra and numbers. So I already talked to you about a certain example. Imagine the seats in your class at the new building. There is a certain order to it. So if I have 4 seats in the front row and I'm looking at you guys, or you guys are on your laptops or playing Mobile Legends on your phone in the back or something, and I say like, no, move up to the front, and I'm gonna put Afriza here. Next, I'm going to put Saddam in the next one, and then I have Dito on the next one, and then I have Angeline. No, I can't use Angeline because I already have an A here. Sorry, Angeline. I'm going to use Bagus on this one. The possibilities, the possible ways for me to put you all in a row is 4 times 3 times 2 to 1. We already established that in the previous slide, because there are 4 people that I can put in here. Then I only have 3 people left in the second spot. Then I have 2 people in the third spot, and then 1 last person in the last spot. Straightforward, right? But now what if I have a circular table? And I have 4 spots as well. I'm gonna get it a little bit more tricky. So here, I wanted to put, I don't even remember who I used just now. Give me a sec. Who did I use just now? Afriza, right? Okay. If I put Afriza here, the first one, okay, about these 4 people, there's 4 possibilities. First, I put Afriza here, then I put Saddam in the next one, then I put Dito in the next one, and then I put Bagus in the last one. That's one possibility, right? And if I'm thinking about it, it looks like the same case here, because I want to put 4 people in the first spot, 3 people in the second spot, 2 people in the third spot, and 1 remaining person in the last spot. But let's say when I told you guys to move to this table, and from the first possibility of 4 people, Afriza just happened to choose the seat over here. And next, Saddam still wanted to sit next to Afriza. He sat over here, Dito over here, and then Bagus over here. It looks different, but these are actually the same solution. Because I've only turned you guys around a little bit. I'm just looking at you from a different angle. So these are not 2 different unique outcomes. This is the same outcome. But how many conditions would be equivalent to these 2? How many chairs, like how many initial conditions could happen? How many options does Afriza has as the first person to sit down for a chair? He could have sat at the top, he could have sat at the right, he could have sat at the bottom, and he could have sat at the left, right? So there are 4 different choices that Afriza could have taken in the beginning, and it would, and if Saddam and Dito and Bagus followed the same pattern, it would just mean the same thing. So in the case of a circular permutation, I'm no longer talking about 4 times 3 times 2 times 1, because there is a certain set of solutions that is equivalent, which is the initial state. So instead of 4 times 3 times 2 times 1, in this case, I only remain with 3 times 2 times 1. And I no longer can compute it using 4 factorial, but instead I have 3 factorial, which is actually n minus 1 factorial. N is the number of people I had, right? 4 people. So if I now go to the mathematical definitions, the left side here, I have circular permutation, which is indeed just like what I explained. It is n minus 1 factorial. But it does consider that if I go around to the clockwise and counterclockwise, it would be different. So in this case here, if after Afriza sat on the top here, Saddam decided to sit on the left side, then that would be a different case. But when I'm talking about ring permutation, it does not consider them to be different. So either way, I'm going clockwise or counterclockwise, it is the same solution. Thus, we use a different formula. Oops, why is this empty? Nothing. Okay, so up until now, we've looked at some different mathematical principles that you probably already know that we are going to utilize to define our sample spaces and the number of outcomes. If you recall, there's a multiplication rule, we have permutations, we have factorials, we have combinations, and lastly, we have circular and ring permutations. Any questions? Not yet? Okay, if we don't, then I'm going to continue with the conditional probability and Bayesian rule. I was going to give you a break now, but since I've seen the clock, if you don't mind, I think I'll just continue to cover these 2 materials so we can end on time, or maybe 5 or 10 minutes late, because I promised to be finished by 3 o'clock. Is everyone okay with that? Or would you like to have a bathroom break? Anyone? No opinions? No opinions? No?
Also for me.
Sorry? Sorry? Who's saying?
It's all right. Yeah.
It's all right to just continue? Okay, great. Okay, then now we're going to talk about conditional probability. So when I was talking about the probability of it raining today, some of you talked about other conditions, like other other information that we could have. Like, for example, what does the sky look today? Like, I would think there's a bigger probability for it to rain if it was quite dark outside and there wasn't any sunlight, right? But when it's really bright out, right now it's really bright out, so I don't think there is a big probability for it to rain. So these considerations that we have are called conditional probabilities. Like, for example, Angeline, do you think, what is the probability of you getting an A on statistics of probability? What do you think? What's the probability? Come on, be confident.
I don't know.
Let's say 80%, okay?
Okay.
Okay, 80%. But what is the probability of you getting A on Statprob if you know your midterm was 100? Do you think the probability would go up? You know that you got 100 on your midterm.
Yes, I think.
You think so, right? Okay.
Yes.
Everybody remember Angeline's promise, okay? I'm joking. So let's hope that it turns out that way. I'm rooting for you. But there are some things that we use in logic, actually, that if something, then I will believe something else. So you can also write it down mathematically when you're talking about probabilities, that the probability of event E, given that F has already occurred. This is called the conditional probability. We denote it as such, and the way to read it is the probability of E given F. So we already know that F occurs. So what is the probability that E occurs? Like, for example, I already know that the sky is bright right now. Then I consider what's the probability for it to rain today. So please remember this particular equation because this is going to come up a lot. This one here, this is going to come up a lot. P, the probability of E given F equals the probability of E and F. EF here is E and F, a union F, over PF, because we already know that F is going to happen. So our basis is F. Note here that on the right, it says for the probability of F larger than 0. Does anyone want to tell me why we have to define PF is larger than 0? Calculus. Why cannot be 0? What happens when PF is 0?
Division thingy with 0.
Division by 0. That's called dosa besar, which I cannot even translate to
I
English.
guess.
I cannot even translate that to English, right? So please do not divide by 0. That's a dosa besar you're not allowed to do in mathematics. So, and if you think about it logically, so if I say the probability of E given F, so the probability of it's raining given it's dark out. But if I know that the probability of F, in this case, the probability of it being dark out is already 0, I don't think I would think that raining would happen, right? Because the conditioning event is already 0. So that makes no point for me to compute the E because the conditioning event is already not happening. So both mathematically is a big sin, dosa besar, and also logically, it doesn't really make sense for me to compute E given F if I already know F is not going to happen. So here we need to consider some special cases. So when the intersection of EF is an empty set, then obviously it is 0, because if you remember, when the intersection is an empty set, or when the set is empty, then the probability of EF would also be 0. This is one of the axioms we have. So 0 on top divided whatever happens on the bottom, then it would be 0. If I were to draw this particular case, so we have E and F like this. So in this case, when I know that they are not intersecting, then I cannot compute the probability would be 0. So I shouldn't have drawn it like this. I'm sorry. I'll erase it now. So when the intersection of E and F is an empty set, this is drawn over here. When it's an empty set, I know that the probability of its intersection is also 0, and thus the probability of E given F would also be 0. It makes a lot of sense if you look at the Venn diagram, because we know that E and F are mutually exclusive here, right? And we know that they have nothing to do with each other. So I cannot compute the dependency between each other as well. Lastly, when I know that F is a subset of E, I know F is a subset of E, I'll draw it too to make it clear. So here I know that F is a subset of E, as I know this is E, I know that this is F. So here it says, so when I compute the probability of E given F, then it obviously is equals 1, because the probability of E intersection F is F itself. The intersection of E and F in this case is the same as probability of F, and thus it is 100% certainty it will happen. If you look at the Venn diagram, it makes complete sense as well, because when F is a subset of E, and you say that I'm computing E based on F, since I already know that F is happening, then I can also safely say that if F is happening, then E would also happen. So let's look into an example to make it a little bit more clear. Okay, let's look at this. I know 2 different cases. I know that a red die and a blue die are thrown. So the first event that I'm talking about is that the red die has a value of 5. What are the possible cases in this case? Please note that when I say 5, 1, then this is the red die, the first die, and this is the blue die. So all cases in which the red die is 5, 5, 1, 5, 2. So it doesn't really matter to me what the blue die is, as long as the first die is, the red die is 5. And next, we also have a sum of scores where the 2 dice is 6. So the red die plus blue die equals 6. These are all the possible conditions. Once again, this is the red die, this is the blue die. So given F has occurred, what is the probability of E? First, we need to define the probability of every case. So here we have the probability of E. We know that the event E has 1, 2, 3, 4, 5, 6 events in it. So we have 6 here, not 6 events, I'm sorry, 6 possible outcomes. So when I'm throwing 2 die, how many possible outcomes do I have in total? 2 die.
36.
Sorry? 36, right? Where did you get that from?
Because there's 2 dice. So
6 times 6, right? The multiplication rule that we already talked about before. We have 36 or 1, 6. Here we have PF. We have 1, 2, 3, 4, 5 cases. So obviously it would be 5 over 36. Now I need to know PEF, which is also written as PEF. So what is the probability of the intersection happening? So what do they have in common? Only one, right? I think, yes, only this one, right? And this one. So we have 1 over 36. And thus, I think I actually have it here. Oh, sorry. So now I have, I'm just gonna delete everything on this slide then, because it's easier to read than my writing. So here we can compute based on this equation here, which I told you it's going to come up many times, so please do not forget it. The probability of E given F is the probability of E and F over the probability of F, and thus I can compute it as 0.2. As you know, it's not always only talking about two different events. So here we have probability of A given B, which we can compute, as you know here, based on the this equation that I told you is going to come up many, many times, right? This one here. Next, I have the probability of C given AB. So first, I'm computing what's the probability of it raining if I know the sky is dark. Next, what is the probability of my jemuran? I do not know what that is in English. I'm so sorry. Anyone that knows it, please let me know. What is the probability of my jemuran getting wet if it rains? If I had a dark sky. Next, I have what is the probability of me getting really mad at myself if my jemuran was wet, if it rained, if it's dark out today, and so forth, right? I can keep going on. So here I'm talking about the first case. What's the probability of it raining if the sky is dark? Here I'm talking about what is the probability of my jemuran being wet given it's raining and the sky is dark. I can continue this on so many times, but then I can compute this as a chain rule, and the probability, I can compute it as follows. Don't worry here, this is just the, how can I say, I'm deriving this equation here, taking P, A, and B from top. This is P, A, B, P, A given B times B. But don't forget, here, it is the same case for the other way around as well. So now I can have a chain rule of the probability of everything happening given something else. Okay, so for exercise, I'm just going to skip it. Don't forget this is, you can look it up on your own on your slides. So actually looking at this development, I think I would prefer to, I prefer to skip the Bayes rules so that I can go into it with more detail in our next meeting. Is that okay with everyone?
Yes.
Because I do not think I want to rush through it right now. I have 2 more minutes on the clock, but I don't think it's a good idea for me to rush through it right now. Is that okay with everyone? So I can just leave it for next time. Is that fine?
It's okay, Miss.
Is that okay? Okay. If I recall correctly, your next homework about probability will be released next week. So I hope it's not too late, because on Monday it'll be released. On Tuesday, we'll cover the remaining Bayes rule and then continue on to the next material. Does that plan sound okay with you guys?
Yes, Miss.
Okay. You just don't want me to continue, right? Right now? You're laughing. You're not saying anything. So I don't really know what you're thinking. Jerome and Afriza is laughing right now. I don't know. Okay. So I'm going to leave you at that. Don't forget that I'm going to put up a discussion forum at the end of this day for you to at least review up until the conditional probability. After the conditional probability, please read on independently Bayes rule as well as independent independent events, I think, independent events. And next week I have my homework, and I'm going to show you about the Bayesian rule as well as how it can be implemented in some problems. And then we'll go on to random variables. Sound okay? Okay then. So if there are, I'm sorry, I have to ask you, are there any questions? Anything? No questions? Okay. Homework deadline is the first homework. I think it's coming up, right? Next week? No, tomorrow, I think. Yes. Right?
Yes.
So please don't forget that. The deadline for homework 1 is tomorrow. I do believe next week the second one is going to come out. And I think we're going to have time to catch up to that before you have to work on it. Okay, then, if that's it for today, then I'm going